What if every planet, star, and galaxy were quietly turning in the same direction? Tonight, we'll follow that question from Earth's rotation to distant galaxies, uncovering how angular momentum, collisions, and cosmic history shape the way the universe moves. Before we begin, tell us where you're listening from, and if you enjoy peaceful journeys like this, please like the video and subscribe to Sleepy Space. Imagine floating far above Earth on a quiet night, so far away that the planet no longer fills your vision, but turns beneath you like a small blue lantern suspended in blackness. And suppose you are looking down from the side of the North Pole. From there, the continents drift eastward, and Earth appears to rotate counterclockwise, a motion so familiar in diagrams that it can begin to feel like a property of the planet itself, as though counterclockwise were somehow written into the stone, water, and atmosphere. Yet, if you continued your slow journey around the globe and viewed the same planet from beyond the South Pole, nothing about Earth's motion would change, while its apparent direction would reverse. And the same rotation would now look clockwise, revealing the first essential answer to our larger question. In space, left and right are not absolute directions, and neither clockwise nor counterclockwise belongs to an object independently of the observer who describes it. A clock face has a front and a back. A room has a ceiling and a floor, and a map has an agreed-upon top. But the universe supplies no universal wall on which every motion can be projected, no cosmic balcony from which all rotations must be judged, and no privileged arrow labeled upward that every civilization would discover in precisely the same way. When astronomers say that Earth rotates counterclockwise, they quietly include a viewing convention. They mean as seen from above Earth's North Pole, where north itself is defined by an adopted astronomical framework rather than by a direction that exists everywhere in nature. The deeper geometry is simple enough to picture, but powerful enough to organize nearly every rotating system in physics. A rotation takes place in a plane, but its orientation is represented by an axis perpendicular to that plane, and physicists encode the direction of this axis with an angular velocity vector, usually written as the Greek letter omega, and with an angular momentum vector, written as L. Curl the fingers of your right hand in the direction of rotation, and your thumb points along the positive axis. Viewed from the tip of that thumb, the motion appears counterclockwise, while viewed from the opposite end, it appears clockwise. This right-hand rule is not a hidden preference of the universe for human anatomy. It is a convention that keeps cross products, coordinate systems, and rotational equations internally consistent. For a particle moving around a chosen origin, angular momentum is written L equals r cross p, where r is the position vector and p is linear momentum, and the cross product creates a vector perpendicular to the plane containing them. For a rigid body turning around a principal axis, the simpler relation L equals I omega often applies, with I representing the moment of inertia, a measure not merely of how much mass exists, but of how far that mass lies from the axis. Two disks with equal mass and equal angular speed can therefore carry different angular momenta if one places more of its material near the rim. And this distinction will later matter when we ask how stars, planets, disks, and galaxies inherit and redistribute rotation. Yet even this clean vector language contains a subtlety. Angular momentum is not an ordinary polar vector like displacement or velocity. It is an axial vector, sometimes called a pseudovector, because under a mirror reflection, it transforms differently from an arrow pointing from one place to another. A mirror can exchange left-handed and right-handed coordinate systems, reversing ordinary spatial handedness, while an axial vector preserves a relationship tied to the orientation of a plane. This is why rotation is connected to chirality, the mathematical distinction between a configuration and its mirror image. But chirality does not create a universal left or right for the cosmos. It only tells us that once a coordinate system and orientation have been chosen, some arrangements cannot be superimposed on their reflections without changing the system. In classical mechanics, this freedom of orientation belongs to a broader symmetry. The laws of physics are invariant under rotations of the coordinate axes. If a sealed laboratory is turned to face another direction, the equations governing falling masses, springs, pendulums, electric charges, and atomic transitions do not acquire new terms merely because the laboratory now points toward a different constellation. Through Noether's theorem, developed by Emmy Noether in the early 20th century, continuous rotational symmetry is linked to the conservation of angular momentum. The calm persistence of a spinning planet or collapsing cloud is therefore connected to one of the deepest structural ideas in modern physics. When the laws do not favor one spatial orientation over another, angular momentum is conserved in an isolated system. Earlier thinkers had already struggled with whether space possessed motion and direction of its own. Newton proposed absolute space, a stage existing independently of matter, and his rotating bucket argument suggested that rotation could be detected through the curved surface of water, even without reference to nearby objects. Leibniz argued instead that space should be understood through relations among things, and Ernst Mach later wondered whether inertia might somehow arise from the distribution of matter in the universe. Einstein was influenced by these questions, although general relativity did not simply convert Mach's idea into a finished law. It replaced the fixed Newtonian stage with dynamical spacetime, whose geometry is shaped by matter and energy. Local observers can still define axes, measure rotation, and carry gyroscopes, but comparing directions across curved spacetime is more delicate than drawing parallel arrows on a flat page. A gyroscope orbiting a massive body may slowly change its orientation through geodetic precession, and a rotating mass can drag nearby inertial frames slightly through frame dragging. These effects do not establish a cosmic left or right. They show that the comparison of directions at separated locations can depend on the path through spacetime and on the gravitational field along that path. Even on Earth's curved surface, an arrow carried around a closed route can return pointing differently without being deliberately turned. And curved spacetime extends this quiet geometric surprise into 4 dimensions. The absence of absolute left and right also forces care when reading astronomical images. A spiral galaxy that appears to wind clockwise in a telescope photograph would appear to wind counterclockwise from the opposite side of its disk, and an image can be flipped by optics, processing, or display conventions unless its orientation is recorded. More importantly, the apparent winding of spiral arms does not always reveal which edge is nearer or which way the material truly rotates. Astronomers often combine images with Doppler measurements, dust lane geometry, and models of spiral structure to reconstruct the three-dimensional motion. The same caution applies to planetary orbits. An animation shown from above the north side of the solar system makes the planets travel counterclockwise, but an observer beneath the orbital plane would see them travel clockwise, while an observer almost within that plane would see the orbits compressed into narrow lines, making both labels nearly useless. What remains meaningful is the geometric relationship among angular momentum vectors. Whether two axes are aligned, opposed, or tilted by a measurable angle. Their dot product provides a clean comparison, because the cosine of the angle between two vectors tells us whether they point generally together, lie at right angles, or point in opposite directions. This is why astrophysicists speak of prograde and retrograde motion relative to a chosen reference axis. A prograde orbit carries angular momentum broadly aligned with the reference system, while a retrograde orbit carries it broadly opposed. And neither term means anything until the reference has been named. For a moon, the reference may be the spin of its planet. For a planet, it may be the orbital angular momentum of the planetary system. For a star, it may be the net rotation of the galactic disk. The universe is therefore not deprived of direction, but direction exists relationally, from one object, plane, field, or observer to another. This distinction is easy to overlook because human perception evolved near a planetary surface where gravity gives us a persistent down, the horizon gives us a stable plane, and our bodies divide experience into left and right. We carry that architecture into the sky, then wonder which side of the universe is up, which way it turns, and whether distant worlds obey the same orientation. Physics answers with a gentler and more exact picture. There are countless axes, countless planes, and countless local frames, but no confirmed universal viewing platform from which all motion becomes clockwise or counterclockwise at once. Before we can ask whether everything spins the same way, we must replace visual direction with angular momentum. Replace the edge of a picture with a three-dimensional reference frame, and separate an object's spin around its own axis from its orbit around another body. Only then does the confusion begin to resolve, because the next layer of the story is not about left or right at all. It is about how matter acquires angular momentum, how that angular momentum survives collapse, and why objects born from the same ancient cloud so often remember a common direction, even though the universe as a whole does not provide one. Matter does not begin to spin because the universe once turned a hidden crank, nor because space itself whispers a preferred direction into every newborn star. It begins to spin because perfect stillness and perfect symmetry are extraordinarily fragile conditions, and gravity is patient enough to amplify even the smallest departure from them. Imagine an immense molecular cloud drifting through the dark interior of a galaxy, colder than any winter on Earth, stretched across dozens of light years, and filled not with silence in the strict physical sense, but with faint turbulence, uneven density, magnetic fields, passing shock waves, and the slow gravitational influence of neighboring stars and clouds. One region may contain slightly more mass than another. One stream of gas may cross another at a shallow angle, and one side may feel a marginally stronger pull from its surroundings. None of these motions needs to be dramatic. At first, the cloud may possess only a tiny net angular momentum, almost lost beneath random motion. Yet once gravity begins drawing the material inward, that slight imbalance can become the organizing principle of the entire collapse. The mathematical reason is contained in the conservation of angular momentum, expressed for a system as the statement that the time rate of change of angular momentum equals the external torque. dl over dt equals tau. If the total external torque is small, the system cannot simply erase its angular momentum while shrinking. A rough model writes angular momentum as L equals I omega, where I is the moment of inertia and omega is the angular velocity. As the cloud contracts, its characteristic radius decreases, and because the moment of inertia scales approximately with mass times radius squared, a reduction in size usually requires an increase in angular speed if L is to remain nearly constant. This is the same principle seen in a skater drawing in extended arms. But in a star-forming cloud, the process unfolds across distances larger than planetary systems and over hundreds of thousands or millions of years, with gas radiating energy, fragmenting, colliding, and redistributing momentum as it falls. The important distinction is that gravity does not create angular momentum from nothing. It magnifies the dynamical importance of angular momentum already present, while torques from outside and within the cloud continually redistribute it. The deeper origin of that initial angular momentum is therefore not a single answer, but a hierarchy of causes. On cosmological scales, the early universe was extremely uniform, but not perfectly so, and small density fluctuations later grew under gravity into the web of matter from which galaxies and clusters formed. A developing region of matter is rarely a perfect sphere, and the gravitational field around it is rarely aligned exactly with its mass distribution. When the tidal field of neighboring structures pulls unevenly on an irregular protogalactic region, it exerts a torque. This framework, known as tidal torque theory, provides a widely used explanation for how dark matter halos and the galaxies forming within them acquire net angular momentum before and during collapse. In simplified form, the result depends on the misalignment between the inertia tensor of the matter patch and the surrounding tidal shear tensor. If their principal axes were perfectly aligned, the torque could vanish, but realistic structure formation does not generally preserve such precision. The emerging spin of a galaxy is therefore partly a fossil of its environment, produced not by a universal rotation, but by local asymmetry within the growing cosmic web. Later mergers, gas inflows, satellite accretion, and feedback from stars or active galactic nuclei can increase, reduce, tilt, or even reverse portions of that angular momentum, leaving many galaxies with a more complicated rotational history than a single, smooth collapse would suggest. On the smaller scale of a molecular cloud, turbulence provides another reservoir of vorticity and shear. Turbulence does not mean that every parcel of gas circles one common axis. It means that motion exists across a spectrum of scales, from broad flows to smaller eddies. So when a dense core separates from the larger cloud, it inherits a particular sum of these motions. Statistical cancellation removes much of the random component, but rarely all of it, and the surviving imbalance becomes the core's net angular momentum. The core then confronts what astrophysicists historically called the angular momentum problem. Observed clouds contain far too much specific angular momentum to collapse directly into a compact star without shedding or transporting most of it. If every parcel conserved its own angular momentum perfectly as it fell inward, centrifugal support would halt the collapse long before stellar densities were reached. Nature proceeds by allowing angular momentum to move outward while mass moves inward. Collisions between gas particles convert ordered motion into heat, and radiation carries energy away. But energy loss alone cannot eliminate total angular momentum. Instead, gravitational torques, spiral density waves, turbulent stresses, and magnetic fields transfer angular momentum between regions. A rotating, flattened disk forms because motion perpendicular to the developing midplane is more easily damped by collisions, while motion around the central axis persists. Gas above and below the plane repeatedly crosses denser material, shocks, loses vertical kinetic energy, and settles. Yet the azimuthal component remains protected by angular momentum conservation. The result is not a rigid plate, but a differentially rotating disk in which inner material circles faster than outer material, following approximately Keplerian motion when the central mass dominates, with orbital speed scaling as the inverse square root of radius. This shear is essential because neighboring rings must exchange angular momentum if accretion is to continue. In many theoretical treatments, the complex transport is represented by an effective viscosity, though ordinary molecular viscosity is far too weak to explain most astrophysical accretion rates. In sufficiently ionized disks, the magneto-rotational instability can drive turbulence by linking fluid elements through magnetic tension, allowing inner gas to lose angular momentum and spiral inward, while outer gas gains it and drifts farther away. In cooler or weakly ionized regions, gravitational instability, disk winds, hydrodynamic turbulence, and large-scale magnetic braking may become important, with their relative roles still depending on temperature, ionization, field geometry, disk mass, and evolutionary stage. Magnetic braking is especially subtle. Field lines threading a collapsing core can connect rapidly rotating inner material to a more slowly rotating envelope, carrying angular momentum outward through magnetic stresses. At the same time, magnetically launched jets and winds can remove angular momentum from the star disk system altogether by expelling a comparatively small amount of mass with a disproportionately large lever arm. These narrow outflows, visible across star-forming regions, are not merely decorative beams cutting through nebulae. They are part of the mechanism that permits matter to continue falling inward without forcing the young star to spin itself apart. Even after a star forms, its rotation keeps evolving. Contraction tends to spin it up. Accretion can add angular momentum. Magnetic coupling to the disk can regulate the rate, and stellar winds can gradually spin it down over billions of years. Planets assembling within the surrounding disk inherit the dominant orbital direction because they are built from material already circling the same star. But their individual spins arise from a more local and chaotic accounting of impacts, accretion streams, internal differentiation, and tidal evolution. A protoplanet, growing through many small collisions, may develop a preferred spin statistically related to the disk. Yet, a late giant impact can tilt or reverse that spin, without reversing the planet's orbit. Thus, the common direction seen in many planetary systems is not proof that matter everywhere began with the same orientation. It is evidence that nearby objects shared a rotating birthplace. There is also a useful boundary to draw between macroscopic rotation and quantum spin. Electrons, protons, and other particles possess intrinsic angular momentum, called spin. But this is not accurately pictured as tiny solid spheres physically turning in space, and it is not the source of a molecular cloud's bulk rotation. Quantum spin and orbital angular momentum obey related mathematical rules, yet the rotation of stars, disks, and galaxies emerges from the collective motion and distribution of enormous numbers of particles under gravity, electromagnetism, fluid dynamics, and external torque. Seen across the full range of scales, matter begins to rotate not because rotation is imposed from one cosmic center, but because collapse selects and magnifies tiny asymmetries, because neighboring structures pull unevenly, because turbulence leaves residual motion, and because angular momentum can be transferred far more readily than it can be destroyed. What appears from a distance as a serene spinning disk is therefore the visible resolution of a long negotiation. Mass moving inward, momentum moving outward, magnetic fields tightening and releasing, shocks erasing some motions while preserving others, and gravity quietly transforming imperfection into order. This is why so many systems spin, and also why they do not all spin the same way. Each rotation is a local memory of how matter arrived, what pulled upon it, what collided with it, and which pathways allowed it to surrender energy without surrendering the angular momentum that shaped its final form. Seen from a quiet point above the sun's north pole, the solar system appears almost ceremonial in its order. 8 planets moving around the same star in the same counterclockwise direction, their paths spread across a broad but remarkably thin disk, as though the entire family had once listened to a single ancient instruction and continued obeying it for more than 4.5 billion years. Mercury circles closest to the solar furnace. Venus follows through its dense veil of clouds. Earth carries its oceans and sleeping continents. Mars moves through colder light. And far beyond them, the giant planets travel with slower dignity. Yet all 8 complete their revolutions in the same orbital sense. This agreement is not a coincidence, and it is not evidence that the whole universe possesses one preferred direction. It is the surviving geometry of a shared birth. Long before planets had names, the matter that would become the Sun and its surrounding worlds occupied part of a cold molecular cloud composed mainly of hydrogen and helium, enriched by heavier elements forged in earlier generations of stars. A disturbance, perhaps associated with turbulence, nearby stellar activity, or the cloud's own gravitational instability, allowed one dense region to contract. The precise trigger for the Sun's formation cannot now be reconstructed with certainty, but the larger physical sequence is well established. As the region collapsed, its small net angular momentum became increasingly important, the central concentration grew hotter and denser, and the infalling material flattened into a rotating disk. This general picture developed historically from the nebular ideas of Immanuel Kant and Pierre-Simon Laplace in the 18th century, although the modern solar nebula model differs greatly from their early proposals because it incorporates thermodynamics, plasma physics, isotope evidence, computer simulations, and direct observations of disks around young stars. The key prediction remains beautifully clear. Planets assembled within one rotating disk should inherit a common orbital direction and should occupy roughly the same plane. The solar system displays both signatures. The reference plane commonly used is the ecliptic, defined by Earth's orbit, and the other major planets remain close to it, though not perfectly upon it. Their orbital inclinations differ by several degrees, with Mercury noticeably more tilted than most, while the dwarf planets and small body populations exhibit a much wider range. This slight disorder matters because a perfectly flat system would be physically suspicious. Real disks are turbulent, gravitationally active, and repeatedly disturbed by growing bodies. So the near alignment of the planets is not the absence of history, but the residue left after a history that was never perfectly smooth. Their orbits are also elliptical rather than circular, following the laws Johannes Kepler inferred from Tycho Brahe's observations and Isaac Newton later explained through universal gravitation. For an ideal two-body system, the orbital angular momentum vector remains fixed and perpendicular to the orbital plane. But the solar system is not a collection of isolated pairs. Every planet perturbs every other planet, producing slow changes in eccentricity, inclination, and orbital orientation. These secular interactions unfold over timescales far longer than a human life and can be treated through perturbation theory or numerical integration, revealing that planetary orbits breathe and precess without abandoning the system's broad architecture. The agreement among the planets is therefore dynamic rather than rigid, more like a group of distant lanterns drifting along neighboring currents than beads fastened to a solid wheel. The Sun itself preserves another part of the original pattern. It rotates in the same general sense as the planet's orbit, and because it is made of plasma rather than solid material, different solar latitudes rotate at different rates, with the equatorial regions completing a turn more quickly than regions nearer the poles. The Sun's spin axis, however, is tilted by roughly 7 degrees relative to the normal of Earth's orbital plane, a modest but scientifically important misalignment. Possible explanations include torques from the protoplanetary environment, early interactions with companion stars in the Sun's birth cluster, magnetic coupling between the young Sun and its disk, or changes produced by the evolving distribution of planetary angular momentum. No single explanation is universally established, yet the tilt reminds us that common origin does not require exact geometric perfection. The distribution of angular momentum adds another layer of subtlety. The Sun contains more than 99% of the solar system's mass, but it carries only a small fraction of the system's total angular momentum when the planet's orbital motion is included. Much of that angular momentum resides in the orbits of Jupiter and Saturn because angular momentum depends not only on mass, but also on orbital distance and speed. In simplified form, the orbital angular momentum of a planet on a nearly circular orbit scales as mass times the square root of the product of the Sun's gravitational parameter and orbital radius. A massive planet far from the Sun can therefore dominate the angular momentum budget even while the Sun dominates the mass budget. This apparent imbalance was once a serious challenge for early nebular theories. A collapsing cloud that placed nearly all its mass at the center somehow had to leave much of its angular momentum in the surrounding disk. Modern models address this through magnetic braking, disk winds, gravitational torques, viscous-like stresses, and the transfer of angular momentum between inward-moving and outward-moving material. Planet formation itself continued this redistribution. Microscopic dust grains collided and adhered, larger aggregates formed, planetesimals emerged, and gravitational focusing allowed some bodies to grow more rapidly than others. In the inner solar system, where temperatures were too high for abundant volatile ices, rocky planets assembled from silicates and metals. Farther out, icy materials increased the available solid mass, helping the cores of giant planets grow before capturing or retaining large gaseous envelopes. Throughout this process, nearly every building block was already moving around the young sun in the same dominant direction. So prograde orbital motion was not chosen separately by each planet. It was inherited from the disk's collective flow. The planet's axial spins developed less uniformly. Accreting material delivered angular momentum, but the exact spin of a growing world depended on the timing, size, angle, and velocity of impacts, as well as on later tidal evolution. For this reason, orbital direction offers a cleaner record of the original disk than planetary rotation does. Mercury, Earth, Mars, Jupiter, Saturn, and Neptune rotate in the broadly prograde sense, yet their rotation periods and axial tilts differ dramatically. Jupiter turns once in roughly 10 hours despite its immense size, producing a noticeable equatorial bulge and powerful atmospheric banding. Saturn rotates comparably quickly, though determining a precise internal rotation period is complicated because its visible atmosphere does not behave like a solid surface, and its magnetic field is unusually axisymmetric. Earth's approximately 24-hour day has been lengthened over geological time by tidal interaction with the Moon, while Mars completes a rotation in a little more than 24 hours, but carries an axial tilt that varies more strongly because it lacks a large stabilizing moon. Mercury presents a different kind of order. It is not tidally locked in the simple one rotation per orbit state once assumed. Instead, it occupies a 3-to-2 spin-orbit resonance, rotating 3 times for every 2 revolutions around the Sun. This state results from the combination of Mercury's eccentric orbit, its permanent equatorial asymmetry, and solar tidal torques, demonstrating how a planet can retain prograde spin while settling into a highly specific rotational rhythm. Even the planet's orbital spacing contains memories of migration rather than static placement. The giant planets likely did not form exactly where they now reside. Gravitational exchanges with gas, planetesimals, and one another may have moved them inward or outward, and families of models, such as the Nice model, explore how an early rearrangement of the outer planets could have shaped the Kuiper belt, scattered smaller bodies, and altered the bombardment history of the inner solar system. Details remain under study, but migration is now a central element of planetary science because observations of exoplanetary systems show that planets can travel far from their birth locations. The solar system's present calm may therefore be the late surface of a more restless youth. Its planets still move in one dominant orbital direction because migration usually changes orbital size and shape more easily than it reverses the sign of angular momentum for a massive planet embedded in the same system. Reversing an entire planetary orbit would require an enormous dynamical intervention, whereas tilting an axis or scattering a smaller body is comparatively easier. This asymmetry explains why the solar system can appear strongly unified at the planetary level, while becoming increasingly diverse among moons, asteroids, comets, and distant objects. The 8 planets preserve the broad handwriting of the solar nebula: shared direction, approximate coplanarity, and nearly circular orbits. Their differences preserve the later annotations: collisions, resonances, tides, migration, and mutual perturbations. So when the solar system seems to answer that everything is turning the same way, it is telling only a local and carefully qualified truth. The major planets do agree on the direction of their journey around the Sun, because they were assembled inside one rotating disk. But they do not rotate identically. They do not occupy one mathematically perfect plane, and they do not move as pieces of a rigid mechanism. Their order is statistical, inherited, and slowly evolving. It is the order of common ancestry rather than universal command, and just beyond that apparent harmony wait the worlds whose axes have been overturned, whose spins have been slowed or reversed, and whose existence reveals how easily the first direction of a planet can be rewritten without disturbing the larger orbit that still carries it through the night. Venus and Uranus move around the Sun in the same broad orbital direction as the other planets. Yet each carries a rotational history so unusual that they seem, at first glance, to have stepped outside the quiet agreement of the solar system. And this apparent rebellion is exactly what makes them scientifically valuable. Because a planet that turns strangely is not breaking the laws of physics, but preserving evidence of forces that acted upon it long after the original protoplanetary disk had established the common direction of planetary motion. Venus offers the more deceptive case. Its orbit is ordinary by solar system standards. It travels around the Sun counterclockwise when viewed from above the Sun's north pole, completing one revolution in about 224.7 Earth days. But the solid planet rotates in the opposite sense, so slowly that one sidereal rotation takes about 243 Earth days. Its day, measured against the distant stars, is therefore longer than its year, although the interval from one sunrise to the next is shorter, about 116.75 Earth days, because the planet's retrograde spin and prograde orbital motion work together to alter the solar cycle. From the surface, beneath clouds thick enough to hide the stars and a carbon dioxide atmosphere nearly 90 times the pressure of Earth's at sea level, the Sun would appear to rise in the west and descend toward the east, moving with such patience that entire human lifetimes could be imagined within a single passage of daylight. Yet the direction of Venusian rotation is more subtle than the simple statement that Venus is spinning backward. A planet's orientation is described by the angle between its spin axis and the normal to its orbital plane, and Venus is often assigned an obliquity near 177 degrees, which means its angular momentum vector points almost opposite the orbital angular momentum vector. The same physical state could be described geometrically as an axis tilted only a few degrees, while the body rotates in the reverse sense. And this ambiguity reminds us that upside down and backward are partly matters of convention. The measurable fact is that the spin and orbital angular momentum vectors are nearly anti-aligned. How Venus arrived there remains an open problem, not because physics lacks possible mechanisms, but because several processes can produce similar final states while erasing much of the evidence needed to distinguish among them. A large impact during the violent era of planet formation could have altered the planet's spin angular momentum, perhaps slowing, tilting, or reversing its rotation. But a single collision is not automatically sufficient as an explanation. The final spin depends on the impactor's mass, velocity, angle of approach, and the state of Venus at the time, while later tidal evolution could substantially modify whatever rotation remained. The Sun raises gravitational tides in the body of Venus, deforming it slightly and exerting a torque that tends to reduce differences between the planet's rotation and a tidally favored state. Because Venus is relatively close to the Sun and rotates slowly, these torques have had billions of years to act. Its massive atmosphere introduces another influence rarely important at the same scale on rocky worlds. Solar heating creates atmospheric thermal tides, large pressure patterns that move through the atmosphere and exchange angular momentum with the solid planet. The gravitational tide in the solid body and the thermal tide in the atmosphere can act in opposing ways, allowing stable or slowly evolving rotational equilibria that would not exist on an airless planet. Models involving core mantle friction, atmospheric circulation, and the planet's internal dissipation add further complexity. And some calculations show that a slowly rotating retrograde state can emerge through long-term evolution without requiring one perfectly aimed impact to reverse a formerly rapid prograde spin. Other models retain giant impacts as important initial conditions, followed by solar and atmospheric torques that guide Venus toward its present rotation. The scientific caution is essential. The retrograde state is known, but the exact pathway is not. Venus may not have forgotten its original direction in one sudden moment. It may have surrendered that direction gradually, through a long conversation between sunlight, atmosphere, rock, and gravity. The planet's current rotation is also not perfectly constant. Spacecraft radar measurements have found small variations in the length of the Venusian day, likely associated with exchanges of angular momentum between the atmosphere and the solid surface, much as winds and seasonal mass movements cause tiny changes in Earth's rotation, though the Venusian effect is more prominent because the atmosphere is so massive and the rotation so slow. Even now, then, the planet's spin is not a frozen relic, but a living, dynamical quantity. Far beyond Venus, where sunlight has weakened and the orbital year stretches to 84 Earth years, Uranus presents an even more dramatic geometry. Its axial tilt is about 97.8 degrees, so its spin axis lies almost within the plane of its orbit. Rather than turning upright like Earth or Jupiter, Uranus appears to roll around the Sun on its side, with one pole, then the other, aimed broadly toward the Sun during different parts of its long year. Because its obliquity exceeds 90 degrees, its rotation is classified as retrograde relative to its orbital motion, though it is often more intuitive to imagine a prograde planet tipped beyond the vertical until its angular momentum vector points into the opposite hemisphere. This extreme tilt creates seasons unlike those of any other major planet. Near solstice, one pole can remain in sunlight for roughly 21 Earth years, while the opposite pole remains in darkness. And around equinox, the sun shines more directly over the equatorial regions as the planet's rings appear edge-on from some viewing geometries. The atmosphere does not respond in a simple way to this slow seasonal forcing, because Uranus also emits unusually little internal heat compared with the other giant planets, and its circulation is governed by radiative timescales, methane absorption, cloud dynamics, and deep atmospheric processes that remain incompletely understood. The familiar explanation for Uranus's tilt is a giant collision with a planetary embryo early in solar system history. Such an impact could, under suitable conditions, deliver enough angular momentum to overturn the planet's spin axis, and numerical simulations have explored impacts by bodies roughly comparable in mass to Earth or larger than Mars. Yet the problem becomes more demanding when the entire Uranian system is considered. The planet's narrow rings and major regular moons orbit close to its equatorial plane, sharing the planet's extreme orientation. If the moons formed before a late impact, the collision would have needed either to tilt them coherently or destroy and reform them from a debris disk aligned with the new equator. If they formed afterward, the impact-generated material would need to reproduce their observed masses, compositions, and orbital architecture. Some simulations suggest that a sufficiently energetic oblique collision could create a disk from which the satellites reassembled, while other studies find difficulties involving heat, volatile retention, or angular momentum distribution. A single impact remains plausible, but it is not the only possibility. Secular gravitational interactions may also tilt a planet gradually. In some models, Uranus could have entered a spin-orbit resonance, in which the precession of its spin axis became linked to changes in its orbital plane, allowing a distant satellite, a massive circumplanetary disk, or interactions with other planets to amplify the obliquity over time. Such mechanisms can, in principle, move a planet toward a large tilt without one catastrophic collision, although achieving nearly 98 degrees within realistic timescales and preserving the satellite system imposes strict conditions. Hybrid histories are also possible. Moderate impacts may have altered the initial spin, while resonant torques later pushed the axis farther, or a gradual tilt may have been completed by a final collision. Current evidence does not compel one unique narrative. What is clear is that Uranus's orbit around the Sun was not reversed. The far greater reservoir of angular momentum associated with its heliocentric orbit remained aligned with the planetary system, while the much smaller angular momentum of the planet's axial rotation was redirected. This difference in scale explains why a world can be turned almost completely on its side without being thrown into a retrograde orbit around the Sun. Orbital angular momentum for a giant planet involves its entire mass moving around the Sun at a distance of billions of miles, whereas spin angular momentum depends on the internal distribution of mass and the rotation about the planet's own radius. An impact or torque powerful enough to alter spin dramatically may still be far too weak to reverse the orbit. Venus and Uranus therefore reveal a hierarchy of memory within planetary systems. The common direction of orbital motion is the deepest and most difficult record to erase, inherited from the protoplanetary disk and protected by the enormous angular momentum of the system. Axial rotation is more vulnerable, shaped by collisions, tides, atmospheric torques, internal friction, resonances, and satellite interactions. A planet may continue traveling faithfully along the ancient current, while its own body turns against that current or lies nearly sideways within it. These worlds do not weaken the nebular model. They make it more complete by showing that formation establishes an initial order while evolution writes over selected parts of it. The solar system's harmony was never a permanent command. It was a starting condition, and Venus and Uranus are the quiet evidence that even a planet can preserve its path around the Sun while losing almost every visible trace of the way it first learned to spin. Beyond the 8 planets, the solar system's apparent agreement begins to loosen, not because the laws of motion become less reliable, but because smaller bodies preserve a wider and more complicated record of capture, collision, migration, fragmentation, and gravitational exchange. And nowhere is this clearer than among the moons, rings, and comets that move through the darkness like fragments of several different histories laid quietly on top of one another. Close to the giant planets, many large moons follow a familiar pattern. They orbit in the same direction that their planets rotate. Their paths are nearly circular, and their orbital planes lie close to the equators of the worlds they circle. This arrangement is not accidental. Jupiter's Galilean moons, Saturn's major inner moons, and the principal moons of Uranus are generally understood to have formed within rotating disks of gas and solids that surrounded the young planets, smaller versions of the protoplanetary disk that once encircled the Sun. In such a circumplanetary disk, matter already possessed a dominant direction of angular momentum. So moons assembled from that material inherited prograde orbits in much the same way that planets inherited their common direction around the Sun. Their present motions are therefore local expressions of shared origin, not evidence of a universal direction extending across space. Even within these ordered systems, however, tidal evolution slowly changes the architecture. A moon orbiting outside a planet's synchronous radius can receive angular momentum from the planet's rotation and move gradually outward, as Earth's moon does, by several centimeters per year, while a moon inside that radius may lose orbital angular momentum and spiral inward. The total angular momentum of the coupled system is conserved to high precision, but its distribution shifts between planetary spin, lunar orbit, internal deformation, and heat. A moon that appears to follow a simple circular path is thus participating in a slow exchange that may continue for billions of years, and its direction alone reveals only one layer of its history. Farther from the planets, the order becomes much less uniform. The outer regions of the giant planet's gravitational domains contain numerous irregular moons with eccentric, steeply inclined, and often retrograde orbits. These objects are unlikely to have formed in the smooth equatorial disks that produced the regular satellites, because a disk naturally damps inclination and eccentricity through collisions and gas drag. Their scattered geometry instead suggests capture, meaning they once traveled independently around the Sun before becoming gravitationally bound to a planet. Capture is not as simple as a passing object falling into a planet's gravity, because in an ideal two-body encounter, energy is conserved and the visitor usually departs with the same excess speed it possessed on arrival. For permanent capture, Energy must be removed from the object's planet-centered motion. In the early solar system, this could occur through gas drag in a planet's extended envelope, through collisions, through the breakup of binary objects, or through three-body interactions in which one body carries away enough energy for another to remain bound. The probability of these processes was greater when the planets were young, surrounded by gas, debris, and migrating planetesimals. Once captured, an irregular moon could remain on an orbit tilted at almost any angle, including one whose angular momentum points opposite the planet's rotation. Retrograde motion in such a case is not a malfunction of the system. It is one of the clearest signs that the moon arrived from elsewhere. Neptune's moon Triton is the most dramatic example. Triton is larger than Pluto and travels around Neptune in a nearly circular retrograde orbit, moving opposite the planet's spin. Its size and composition make it difficult to explain as a small body formed in place within Neptune's original satellite disk, while its retrograde direction strongly favors capture from the trans-Neptunian population. One leading scenario proposes that Triton once belonged to a binary system similar to other paired objects in the Kuiper belt. During a close encounter with Neptune, gravitational forces may have disrupted the pair, ejecting one member while leaving Triton bound. Its first captured orbit would probably have been large and highly eccentric. Tidal dissipation inside Triton and Neptune then removed orbital energy while largely preserving the sign of the angular momentum, shrinking and circularizing the orbit over time. That evolution may have destabilized Neptune's earlier moons, causing collisions, ejections, and the reassembly of debris into the smaller satellites observed today. Triton's smooth modern orbit is therefore not evidence of a peaceful beginning. It may be the final quiet shape left by a deeply violent rearrangement. Saturn's distant moon Phoebe tells a related but smaller story. It moves on a retrograde inclined orbit and differs in composition and appearance from Saturn's large regular moons, supporting the view that it was captured from an outer population of primitive bodies. Dust knocked from Phoebe and related objects forms an enormous, faint ring around Saturn, one that is tilted relative to the bright main rings and shares Phoebe's retrograde sense of motion. This broad structure is so tenuous that it would be nearly invisible to an observer nearby. Yet it demonstrates that even the word ring can refer to dynamically distinct populations with separate origins and orientations. The bright rings of Saturn, by contrast, lie almost exactly in the planet's equatorial plane and consist of countless particles, from grains smaller than dust motes to blocks as large as buildings, or perhaps larger. They do not rotate together like a solid record. Each particle follows its own orbit, and Kepler's laws require the inner material to travel faster than the outer material. If the rings were rigid, this differential motion would tear them apart. But because they are particulate disks, collisions and collective gravitational effects allow them to remain thin while continuously exchanging energy and angular momentum. Spiral density waves move through them, where orbital frequencies resonate with moons. Gaps are opened or maintained by embedded satellites, and small moonlets create propeller-shaped disturbances that reveal unseen masses within the ring plane. Their flatness arises because particle collisions damp vertical motion more effectively than orbital motion around the planet, gradually compressing the system toward the equatorial plane. The Roche limit also shapes their existence. Inside this approximate boundary, tidal forces from the planet can prevent loosely bound material from assembling into a large moon, or can disrupt a vulnerable satellite, although the exact outcome depends on density, internal strength, and orbital conditions. The rings may therefore contain remnants of moons, leftover construction material, material continually replenished by impacts, or some combination of these sources. Their ages remain an active topic of research because estimates depend on contamination rates, mass measurements, particle recycling, and models of long-term evolution. But their direction is less mysterious. Most dense planetary rings move prograde because they formed from material dynamically connected to the planet and its inner satellite system. Comets carry the story farther from the Sun, where the distinction between local order and accumulated chaos becomes even more pronounced. Short-period comets associated with the Kuiper belt and scattered disk often retain some relationship to the solar system's original plane, though gravitational encounters with Neptune can stretch, tilt, and scatter their orbits. Many remain prograde, but the population spans a wide range of inclinations, and individual objects can be placed on highly unusual paths through repeated encounters. Comet Halley, for example, travels around the Sun on a retrograde orbit, inclined by more than 90 degrees to the ecliptic, passing through the planetary region in a direction opposite to the planets. Its motion does not imply that it formed in a disk turning backward. Dynamical models suggest that objects originating in the distant reservoirs of the outer solar system can have their inclinations and eccentricities reshaped over immense periods by planetary perturbations, galactic tides, and passing stars. The most distant proposed reservoir, the Oort cloud, is thought to form a roughly spherical swarm extending thousands or perhaps tens of thousands of astronomical units from the Sun. Its objects likely began closer to the planetary region, where they formed within the same broad disk as the planets, but encounters with the growing giant planets scattered them onto enormous orbits. Weak perturbations from the Milky Way and nearby stars then lifted their perihelia away from the planets and randomized their orbital orientations. The resulting cloud is not perfectly mapped because its members are too faint and distant to observe directly in their resting state. Yet the arrival directions of long-period comets support the idea of a nearly isotropic source. From such a reservoir, a comet may fall inward from almost any direction, crossing the ecliptic from above or below, moving prograde or retrograde, and approaching the Sun on an orbit so elongated that its next return may lie millions of years in the future. These bodies reveal how a system born as a disk can gradually populate a sphere. Gravity first creates local order by gathering material into common planes and directions. Then, gravitational scattering spreads smaller objects across a much broader range of possibilities. Moons, rings, and comets, therefore, do not contradict the solar system's shared origin. They expose the full depth of it. Regular moons remember rotating disks. Irregular moons remember capture. Rings remember fragmentation and tidal confinement. Kuiper belt objects remember the outer edge of planetary formation, and Oort cloud comets remember encounters powerful enough to lift once flat orbits into the darkness surrounding the Sun. The farther we move from the major planets, the less useful it becomes to imagine the solar system as a single wheel. It is instead a layered, dynamical archive with order nested inside disorder, each population preserving a different balance between inheritance and interruption, and every strange direction quietly answering the same question. Not everything moves the same way, because not everything arrived by the same road. The first planets found around other sun-like stars did not resemble the calm arrangement astronomers had expected from the solar system. Instead of distant giants moving through cold, spacious orbits, several were enormous worlds rushing around their stars in only a few days, so close that their upper atmospheres were heated to thousands of degrees. And in that first surprise, the old picture of planetary systems as quiet copies of our own began to dissolve. Today, the confirmed population extends into the thousands. But the deepest lesson is not simply that planets are common. It is that the same laws of gravity and angular momentum can build architectures ranging from nearly flat families of small worlds to solitary giants moving across the equators of their stars at steep angles, and sometimes in the opposite projected direction. A young star is generally surrounded by a rotating protoplanetary disk, and the simplest formation model predicts that planets assembled within that disk should begin on nearly circular, nearly coplanar orbits, with their orbital angular momentum vectors broadly aligned with one another and with the star's spin. Many systems do preserve this restrained geometry. When NASA's Kepler spacecraft watched stars dim as planets crossed their faces, it discovered compact systems in which several planets transit the same star, something that becomes unlikely unless the orbital planes are closely packed together. Statistical studies indicate that a substantial portion of Kepler's multi-planet systems have mutual inclinations of only about 1 or 2 degrees, narrower than the spacing of fingers held at arm's length, although another population may possess larger tilts and remain harder to recognize because only one planet crosses our line of sight. In such systems, the planets move less like isolated wanderers than like grooves in a single ancient record, each orbit preserving the plane of the vanished disk. Resonant chains deepen this impression. When orbital periods form ratios near small integers, repeated gravitational encounters occur at nearly the same phases, and the planets can exchange angular momentum in a regular rhythm. These chains are often interpreted as evidence that planets migrated gradually through gas before the disk dispersed, becoming captured into resonance rather than being thrown violently inward. Yet even a flat system is not perfectly still. Planetary orbits precess. Resonant angles may librate. Eccentricities oscillate, and weak interactions accumulate. So stability means bounded evolution rather than geometrical immobility. The more unsettling architectures appear when the orbital plane of a planet is compared with the equator of its star. A star cannot be resolved as a rotating globe in most exoplanet systems, but its spectrum carries a hidden map. One limb rotates toward Earth and is slightly blue-shifted, while the opposite limb rotates away and is slightly red-shifted. During a transit, a planet first blocks one portion of this rotating surface and then another, creating a temporary distortion in the measured stellar velocity, known as the Rossiter-McLaughlin effect. The shape of that distortion reveals the angle, usually called lambda, between the sky projections of the stellar spin axis and the planet's orbital axis. It does not automatically provide the full three-dimensional angle, because the inclination of the stellar pole toward the observer may remain uncertain. But when combined with stellar rotation periods, projected rotation speeds, asteroseismology, or spot crossing events, the true geometry can sometimes be constrained. This method transformed orbital direction from an assumption into an observable quantity, and the result was a population far more diverse than the early nebular picture alone had suggested. Some hot Jupiters cross nearly along their stars' equators, while others follow strongly tilted, nearly polar, or apparently retrograde paths. Individual measurements have found projected angles close to 180 degrees, indicating that the planet's orbital angular momentum and the star's spin point toward nearly opposite sides of the sky. These planets probably did not condense in their present blisteringly close locations, because, near the young star, the disk may not have contained enough solid material to assemble a giant core easily, and because their current orbits often demand substantial migration. One pathway is disk-driven migration, in which gravitational interactions between a planet and the surrounding gas launch spiral waves and exchange angular momentum, causing the orbit to move inward or outward while usually remaining close to the disk plane. This process can produce close-in planets without strongly tilting them, especially when the disk and stellar equator are themselves aligned. A second family of pathways begins after the gas has thinned, when several massive bodies can interact almost without damping. In planet-planet scattering, close encounters exchange energy and angular momentum, ejecting one planet, widening another orbit, or sending a survivor inward on a highly eccentric and inclined path. If that survivor repeatedly passes very close to the star, tides raised in the planet and star dissipate orbital energy most strongly near periapsis. The semi-major axis and eccentricity then shrink, while much of the orbital angular momentum is retained, leaving a short period nearly circular hot Jupiter whose tilted orientation remembers the earlier instability. A distant companion can drive a related process through secular dynamics. In the quadrupole approximation of the Kozai-Lidov mechanism, an inclined outer star or planet can trade the inner planet's inclination against its eccentricity, allowing the orbit to become extremely elongated before tides circularize it. More complete treatments include octopole terms, general relativistic precession, tidal and rotational bulges, and the back reaction of additional planets, all of which can suppress, reshape, or intensify the evolution. No single mechanism explains every hot Jupiter, and current evidence favors multiple channels whose relative importance may depend on companions, stellar type, age, and initial conditions. The star itself may also be the tilted component. A binary companion can torque a protoplanetary disk away from the stellar equator. Magnetic interactions between a young star and its disk have been proposed as another source of misalignment. Turbulent accretion may deliver material whose angular momentum direction changes with time, and internal stellar processes can alter the orientation of the visible envelope relative to the total angular momentum. Thus, a measured spin-orbit angle does not by itself reveal whether the planet moved, the disk tilted, the star reoriented, or several events occurred in sequence. The temperature of the host star adds another clue, but not a final verdict. Hot Jupiters around cooler stars are often more aligned than those around hotter stars, a pattern that may arise because cool stars possess substantial convective envelopes capable of dissipating tidal energy and reducing obliquity, while hotter stars preserve earlier misalignments more effectively. The exact tidal physics remains uncertain, and newer ideas involving resonance locking between orbital forcing and stellar oscillation modes are being explored as ways to realign some systems without destroying the planets through rapid orbital decay. Warm Jupiters, orbiting farther out where tides are weaker, provide a quieter record of their histories. A recent set of measurements found the examined warm gas giants around single stars to be comparatively well aligned, suggesting that many may have evolved without the violent high eccentricity migration associated with part of the hot Jupiter population, although the sample remains limited and broader surveys are needed. Compact systems of sub-Neptunes also tend to show alignment in the secure measurements obtained so far, supporting the idea that systems containing several nearby planets often preserve their natal disk plane more faithfully than isolated close-in giants. There are important selection effects beneath every comparison. Transit surveys preferentially reveal planets whose orbits happen to pass across their stars from Earth. Radial velocity searches favor massive planets close to their stars, and the Rossiter-McLaughlin effect is easiest to measure for large planets blocking rapidly rotating, bright stars. The observed sample is therefore not a neutral census of every architecture in the galaxy. Even so, the diversity is too strong to dismiss as an observational illusion. Exoplanetary systems show that common formation within a disk creates an initial tendency toward shared direction, but that tendency is a beginning rather than a guarantee. Gas can move planets gently while preserving alignment. Companions can twist entire disks. Resonances can protect orderly configurations. Close encounters can scatter worlds into steep or retrograde paths. And tides can erase eccentricity while leaving inclination as a faint signature of former chaos. Our solar system is not falsely peaceful, but it represents only one surviving outcome among many. Its broad coplanarity suggests that it avoided the most disruptive rearrangements, while other stars carry planetary systems whose present serenity may conceal ejections, collisions, vanished companions, or slow torques acting across billions of years. The farther we look, the clearer the answer becomes. Planets born together often begin by turning together, yet no law requires them to remain forever faithful to that first plane. And the night contains systems where the original disk is still legible, systems where it has been folded, and systems where only one tilted orbit remains to tell us that a once orderly family was rewritten. At this moment, while the room around you feels still and the night appears to rest quietly against the windows, the sun is carrying Earth through the Milky Way at roughly 220 kilometers per second, tracing a vast orbit around the galactic center that takes on the order of 250 million years to complete, so that the last time our solar system occupied something close to its present galactic position, the continents were arranged differently. Dinosaurs had not yet appeared, and the familiar sky of today had not been assembled from the same neighboring stars. This motion is often described as though the sun were a planet circling a much larger central object. But the comparison is only partly correct. The Milky Way is not a rigid disk turning like a wheel, and its stars do not move together as fixed points painted onto a single rotating surface. Each star follows its own orbit through a gravitational field created by the combined mass of luminous stars, interstellar gas, dust, the central bulge, the stellar halo, and the far larger but invisible dark matter halo. The Sun's path is approximately circular when viewed on a broad scale, yet it is not a perfect closed ring. It moves slightly inward and outward relative to the galactic center, oscillates above and below the midplane of the disk, and responds to the shifting gravitational influence of spiral structure, giant molecular clouds, and passing stars. In a static, perfectly symmetric gravitational potential, orbital motion could be described through conserved quantities such as energy and angular momentum. But the real Milky Way contains a central bar, transient spiral patterns, evolving mass distributions, and the accumulated remains of past mergers. So a stellar orbit is better understood as a long conversation with a changing galaxy than as a simple ellipse drawn forever in empty space. The dominant direction of rotation in the galactic disk is nevertheless real. Most stars, gas clouds, and young stellar populations in the thin disk carry angular momentum pointing broadly toward the same side of the galactic plane, because the material from which the disk formed acquired a net angular momentum during the assembly of the galaxy. This common rotation is the galactic equivalent of the shared orbital direction of planets in a protoplanetary disk, although the scales, timescales, and dynamical complexity are immensely greater. A galaxy does not collapse from a single isolated cloud in one uninterrupted event. In the modern framework of hierarchical structure formation, dark matter first gathers into halos, gas falls into these gravitational wells, smaller systems merge into larger ones, and fresh material continues to arrive along filaments of the cosmic web. The net spin of the growing galaxy emerges from tidal torques, asymmetric accretion, and the orbital angular momentum of merging structures, then evolves as later events add material from new directions. The disk that eventually forms is therefore not the expression of one pristine initial rotation, but the surviving average of many contributions, some aligned, some inclined, and some opposed. Within that disk, stellar populations preserve different stages of this history. The thin disk, where the Sun resides, contains much of the galaxy's gas, dust, ongoing star formation, and relatively young stars moving on comparatively low inclination orbits. The thick disk extends farther above and below the galactic plane, and includes older stars with larger vertical motions and broader velocity dispersions. The stellar halo surrounds both in a much more diffuse, roughly spheroidal distribution, where stars follow elongated and highly inclined trajectories that need not share the strong rotational support of the disk. Some halo stars even move in a net retrograde sense relative to the main disk, and such motion is often interpreted as evidence that they were deposited by smaller galaxies captured and disrupted by the Milky Way. Their unusual angular momentum acts like a chemical and dynamical signature, especially when combined with elemental abundances and stellar ages, allowing astronomers to identify remnants of ancient mergers long after the original satellite galaxies have been stretched into streams or dissolved into the halo. The Milky Way therefore does not possess one single direction obeyed by every star. It contains a dominant prograde flow in the disk, surrounded and penetrated by populations whose trajectories reflect different origins. The center of the galaxy adds another layer. At the heart of the Milky Way lies Sagittarius A star, a supermassive black hole containing about 4 million times the mass of the Sun. Yet, this object does not control the orbit of the Sun in the way the Sun controls Earth. At our distance, most of the gravitational pull arises from the total mass enclosed within the solar orbit, not from the central black hole alone. The orbital speed of stars in the outer galaxy remains unexpectedly high compared with what would be predicted from visible matter by itself, producing the nearly flat galactic rotation curve that became one of the major lines of evidence for extended dark matter halos. If most mass were concentrated near the center, orbital velocity would decline approximately as the inverse square root of distance, as it does for planets far from the Sun. But in spiral galaxies, the speed often stays roughly constant over a broad radial range. This suggests that additional mass continues to accumulate with increasing radius, distributed through a vast halo that emits little or no detectable light. The exact particle nature of dark matter remains unknown, but its gravitational influence is central to modern models of galactic rotation and formation. Even the phrase rotation curve can be misleading if imagined too mechanically, because it describes average circular velocities as a function of radius, not the behavior of every star. Stellar velocities include random components, orbital eccentricities, vertical oscillations, resonant trapping, and perturbations from non-axisymmetric structures. The Milky Way's central bar, a long concentration of stars rotating as a pattern, redistributes angular momentum through resonances. Stars near particular orbital frequencies can exchange energy and angular momentum with the bar, changing the sizes and shapes of their orbits while remaining bound to the galaxy. Spiral arms also interact with stars and gas, but they are not permanent material arms rotating like the blades of a fan. If the same stars remained locked inside rigid spiral arms, differential rotation would wind the pattern ever more tightly within a few galactic rotations. Instead, spiral structure is generally modeled through density waves, recurrent transient patterns, or gravitational instabilities whose exact nature may vary among galaxies. Stars and gas can enter an arm, experience increased density and compression, and later emerge from it, while the visible pattern may persist, dissolve, or reform. The spiral is therefore a pattern moving through the stellar river, not necessarily the river itself. Gas behaves differently from stars because gas clouds can collide, shock, radiate energy, and settle into thin, rotating layers, while stars pass through one another almost without direct collision. This difference allows gas to lose orbital energy while retaining or redistributing angular momentum, causing it to move inward, form dense clouds, and create new stars. Supernovae, stellar winds, radiation pressure, and outflows from the galactic center can then push gas outward or suspended above the disk, producing a galactic fountain in which material rises, cools, and returns. Angular momentum is transferred during each stage, and the direction of newly arriving gas may not align perfectly with the old stellar disk. Some galaxies contain counter-rotating gas, counter-rotating stellar disks, or central components whose axes are sharply misaligned with the outer galaxy. Such structures are difficult to produce through smooth evolution in isolation, and often point toward external accretion or mergers. A galaxy can absorb a stream of gas arriving with angular momentum opposite to its own, allowing new stars to form in a disk rotating against the older population. In other cases, two stellar disks of comparable scale coexist while moving in opposing directions, creating an extraordinary configuration in which the galaxy's light appears unified even though its internal motions are divided. These systems show that a galaxy's apparent spin is only the dominant statistical pattern, not an absolute command imposed upon every component. The same principle applies to the Sun's motion. Our solar system participates in the broad rotation of the Milky Way because it formed from gas already moving with the disk. Yet the Sun also has a peculiar velocity relative to nearby stars, and those neighboring stars themselves form moving groups, streams, and resonant structures shaped by the bar, spiral arms, and dissolved stellar clusters. The stellar river around us is not smooth water flowing at one speed, but a layered current filled with eddies, crossings, and ancient debris. On sufficiently long timescales, close gravitational encounters with stars and molecular clouds can gradually alter stellar orbits, a process known as dynamical heating, helping older populations acquire larger random motions and thicker vertical distributions. More massive objects also experience dynamical friction, losing orbital energy and angular momentum as they create gravitational wakes in surrounding matter, which can cause satellite galaxies or massive clusters to spiral inward. None of these processes destroys angular momentum. They move it from one component to another, from ordered rotation into random motion, from orbiting satellites into the dark halo, from a rotating bar into stars at resonances, or from inward falling gas into outward moving material. The Milky Way is thus not merely spinning, it is continuously negotiating where its angular momentum resides. Seen from far above, it may resemble a serene, luminous whirlpool, but serenity at that distance conceals billions of individual trajectories, some aligned with the main flow, some tilted, some eccentric, and some moving against it. We are part of that immense current, carried around the galactic center not by a solid structure, but by the curvature of trajectories inside a shared gravitational field. And this reveals a deeper answer to the question of whether everything turns the same way. Within a galactic disk, much of the matter can share a dominant direction because it shares a history of collapse and accretion. Yet a galaxy is never a single wheel. It is a river made from many rivers, a rotating system assembled through countless arrivals, and every star moving through it carries a small fragment of the galaxy's unfinished past. If we could rise slowly beyond the Milky Way and continue outward until thousands of other galaxies appeared beneath us like pale islands scattered across a black and silent sea, it might seem natural to ask whether those luminous spirals are all turning together, whether their arms are being carried by one immense cosmic current, and whether somewhere beyond the edge of our vision there is a direction that the universe quietly prefers. Yet the first obstacle is hidden inside the image itself, because a galaxy that appears to wind clockwise from one side would appear to wind counterclockwise from the other, even though its physical rotation had not changed at all. The words clockwise and counterclockwise describe a projection seen from a chosen viewpoint. The more fundamental quantity is the galaxy's angular momentum vector, an arrow perpendicular to its rotating disk, whose direction must be reconstructed from three-dimensional evidence. A telescope image alone usually shows only the orientation of spiral arms on the sky, often called apparent-handedness or chirality. And although most spiral arms are thought to trail behind the direction of disk rotation, exceptions, distortions, interactions, bars, dust lanes, and uncertain viewing geometry make arm winding an imperfect substitute for a direct kinematic measurement. To determine how a galaxy actually turns, astronomers examine its spectrum across the disk. Light from stars and gas approaching Earth is shifted slightly toward shorter wavelengths, while light from the receding side is shifted toward longer wavelengths, creating a velocity field that reveals the axis and projected sense of rotation. Integral field spectrographs now divide a galaxy into thousands of spatial elements, allowing the motions of stars and ionized gas to be mapped separately. Yet even this does not always identify which end of the spin axis points toward the observer, unless the near side of the disk can also be inferred from dust, structure, or geometry. The question of whether galaxies turn the same way must therefore be translated into several more precise questions. Are their angular momentum axes randomly distributed? Do neighboring galaxies show correlated spins? Do galaxies align with clusters and filaments? And is there evidence for one preferred orientation across the entire observable universe? On the largest scales, the standard cosmological picture predicts no universal clockwise majority, because the cosmological principle assumes that the universe becomes statistically homogeneous and isotropic when averaged over sufficiently large volumes. Isotropy does not mean that every small region must look identical, or that every pair of galaxies must be unrelated. It means that after local structure is averaged away, no direction should remain fundamentally privileged. Galaxy spins may therefore display environmental patterns without violating the larger principle. Just as leaves caught in nearby eddies can momentarily turn together, while a vast ocean possesses no single global whirlpool. The origin of these local patterns begins before a recognizable galaxy exists. In tidal torque theory, a developing concentration of matter is generally irregular in shape, while the surrounding gravitational tidal field is also anisotropic. And when the principal axes of the region's inertia tensor are misaligned with those of the tidal tensor, an early torque arises. The resulting angular momentum is not produced by an absolute rotation of space, but by gravitational interaction between neighboring density structures. As the cosmic web develops, matter drains from under-dense voids into sheets, from sheets into filaments, and from filaments toward dense knots where groups and clusters grow. Gas and dark matter do not arrive equally from all directions, so a young halo can acquire a preferred spin related to the geometry of its environment. Numerical simulations commonly predict a mass-dependent tendency, sometimes described as a spin transition. Lower mass galaxies, or halos, may more often have spin axes roughly parallel to nearby filaments, while more massive systems, shaped by repeated mergers and accretion along the filament, may become more perpendicular. Although the transition mass and strength of the signal depend on simulation methods, galaxy definitions, feedback prescriptions, redshift, and the way filaments are identified. Observations broadly support the idea that the cosmic web can influence galaxy orientation, but they have not yet produced one perfectly uniform result. A three-dimensional study using spatially resolved stellar kinematics from the MANGA survey found statistically meaningful relationships between galaxy spin and cosmic filaments, while later surveys and analyses reported that the signal can depend on mass, morphology, bulge fraction, gas content, activity, and distance from the filament. A 2025 analysis of 2,861 nearly edge-on galaxies found a significant tendency for spin axes to align along filament directions. Yet the authors also noted that earlier observational and modeling results remain contradictory, a reminder that sample selection and reconstruction methods can alter the apparent pattern. These correlations are subtle statistical preferences, not commands obeyed by every galaxy. A filament may contain some galaxies spinning roughly along its length, others spinning across it, and many whose orientations fall between those limits. The reason is historical. Smooth gas accretion can build angular momentum coherently, while mergers can redirect it. Satellite encounters can tilt a disk, and newly arriving gas can rotate differently from the stars already present. Some cosmic filaments themselves have been reported to show coherent rotational motion when galaxy velocities are stacked around their long axes, and hydrodynamic simulations have produced qualitatively similar signals, though quantitative comparisons remain sensitive to how the structures and their dynamical temperatures are defined. Even if such filament rotation is confirmed across broader samples, it would still describe motion within particular structures rather than a shared rotation of the entire universe. Galaxy pairs provide an even smaller scale illustration. Two galaxies formed in the same tidal field or interacting gravitationally may develop correlated orientations, while mergers can convert orbital angular momentum into internal spin. In a cluster, central galaxies often align in shape with the surrounding distribution of matter, and there is emerging evidence that their spins can also correlate with the angular momentum of their host groups. But dense environments simultaneously increase the frequency of encounters capable of scrambling earlier alignments. Local agreement can therefore be both created and erased by the same gravitational hierarchy. The most controversial part of the subject begins when apparent clockwise and counterclockwise spiral galaxies are counted across enormous sky surveys. If their distribution contained a robust dipole, with one-handedness favored toward one side of the sky and the opposite-handedness favored in the other, it might suggest an unexpected large-scale anisotropy, an observational systematic, or some relation between galaxy classification and our own viewing motion. Several studies have claimed statistically significant asymmetries in Sloan Digital Sky Survey, Pan-STARRS, Hubble, and JWST samples, including a small JWST deep field study in which 24 of 34 classified spirals had one apparent handedness and 10 had the other. Those results are intriguing, but they have not established a scientific consensus. Apparent handedness is unusually vulnerable to subtle biases. Human classifiers can prefer one winding direction, image pipelines may mirror fields, automated algorithms may respond differently to brightness and arm structure, survey footprints cover the sky unevenly, neighboring galaxies are not statistically independent, and significance can be exaggerated when an axis is selected after examining the data. A comprehensive 2024 analysis gathered publicly available handedness catalogs and tested dipole and quadrupole anisotropy with both Bayesian and frequentist methods. It found all examined datasets consistent with isotropy within 3 standard deviations and argued that some stronger contrary claims arose from biased or inappropriate statistics. Subsequent debate has continued, with proponents of asymmetry challenging those statistical procedures and presenting additional catalogs. So the responsible conclusion is neither that every reported anomaly is meaningless, nor that a rotating cosmos has been discovered. The evidence currently does not demonstrate, to broad scientific acceptance, that spiral galaxies across the observable universe share one preferred sense of rotation. This distinction between local alignment and global handedness is the heart of the answer. Galaxies are not placed into space like isolated coins tossed at random, because they grow inside a connected network whose tides, filaments, mergers, and gas flows leave measurable correlations. Yet neither are they gears inside a single machine whose teeth all move around one universal axle. Their spin vectors remember regional conditions, the direction from which matter arrived, the gravitational field of nearby structures, the number and geometry of mergers, and the later disturbances that tilted or rebuilt their disks. When those histories are compared across a filament or cluster, patterns can emerge. When the view expands across billions of light years, those patterns are expected to change direction, overlap, and largely average away. So the literal answer is no. Galaxies do not all rotate in the same direction. Some neighboring systems may share statistically related orientations. Particular environments can encourage parallel or perpendicular alignments, and unresolved claims of large-scale handedness remain worthy of careful testing. But no confirmed cosmic arrow presently instructs every galaxy how to turn. The night is filled not with one enormous wheel, but with countless rotating islands, each carrying angular momentum gathered from its own region of the cosmic web. Their motions related enough to reveal how structure formed, yet diverse enough to preserve the universe's deeper absence of any known universal left or right. To ask whether the universe itself may be rotating is to ask a question stranger than whether planets circle stars or galaxies turn within dark matter halos. Because the universe is not an object resting inside a larger room, where an observer might step outside, look back, and watch the whole structure complete a revolution against a fixed background. It includes the space in which distances are defined, the clocks by which change is measured, and every physical reference frame available to us. So before cosmic rotation can become a scientific hypothesis, the familiar image of a sphere spinning through emptiness must be replaced by the more careful language of space-time geometry. The expansion of the universe is not itself a rotation. In the standard cosmological description, sufficiently distant galaxies recede because the scale of space between widely separated, gravitationally unbound regions changes with time, represented mathematically by a scale factor commonly written as A of t. This expansion has no observed central point from which all galaxies were launched, and the Big Bang is not treated as an explosion occurring at one address inside pre-existing space. Every region of the observable universe traces its history toward an earlier state that was hotter and denser, so there is no known central axle around which the cosmic contents must turn. A rotating cosmology, if nature possessed one, would therefore not necessarily resemble a carousel circling a point. It would mean that the large-scale flow of matter, or the geometry used to describe that flow, contained non-zero vorticity, a measurable tendency for neighboring world lines to twist relative to locally non-rotating gyroscopes. In relativistic cosmology, the motion of a cosmic fluid can be decomposed into several parts. Its expansion scalar describes how a small volume changes size. Its shear tensor describes how that volume is stretched differently along different directions. Its acceleration records whether the flow follows freely falling paths, and its vorticity tensor describes local rotational twisting. A perfectly homogeneous and isotropic Friedmann-Lemaitre-Robertson-Walker universe has expansion, but no background shear or vorticity. This is not a conclusion forced by Einstein's field equations alone. It is a symmetry assumption whose remarkable success must be tested against observation. General relativity permits far more varied geometries, including universes that expand at different rates along different axes, universes with large-scale shear, and mathematical solutions containing global rotation. The field equations relate space-time curvature to energy and momentum, but they do not insist that every physically imaginable universe resemble the nearly isotropic one we observe. This freedom became dramatically clear in 1949 when Kurt Gödel presented a rotating solution to Einstein's equations containing pressureless matter and a negative cosmological constant. In Gödel's spacetime, rotation is woven into the relation between matter and inertial frames, and the geometry allows closed, time-like curves, paths that in the mathematical model can return to an earlier event. The solution remains historically profound because it showed that general relativity permits causal structures far removed from ordinary intuition, but it does not resemble the measured expansion, matter content, or large-scale thermal history of our universe, and it is not regarded as a realistic description of the cosmos. Later, Gödel-type and expanding rotating models have been developed to explore whether rotation can coexist with expansion under more plausible conditions, while Bianchi cosmologies provide a systematic classification of spatially homogeneous but potentially anisotropic universes. Some Bianchi models possess shear without ordinary rotation. Some contain vorticity, and some generate swirling or spiral-like signatures across the sky. Their importance is not that one of them must replace standard cosmology, but that they provide controlled mathematical alternatives whose predicted patterns can be sought in real data. A genuinely rotating universe would be expected to leave more than a philosophical impression. It could establish a preferred cosmic axis, alter the relation between distance and recession velocity in different directions, influence the growth and orientation of structure, rotate or distort patterns of radiation, and imprint a coherent temperature and polarization signature upon the cosmic microwave background. The CMB is especially powerful because it comes from the era when the universe first became transparent, roughly 380,000 years after the beginning of cosmic expansion, and it reaches us from every direction as an almost uniform bath of microwave radiation. Its small temperature fluctuations, only a few parts in 100,000 across much of the sky, contain information about the density, motion, geometry, and gravitational potentials of the young universe. If a strong global rotation or shear had been present, it would generally have created a highly organized directional pattern, rather than the nearly statistically isotropic field measured by missions such as WMAP and Planck. Some Bianchi Type 7H templates can produce spiral-like temperature structures that visually resemble certain large-angle features in CMB maps, and for a time, this resemblance encouraged speculation that cosmic rotation might explain anomalies such as hemispherical power differences, unusual alignments among low multipoles, or the region known as the cold spot. Yet resemblance is not enough. A physically consistent model must fit the ordinary acoustic fluctuations, the polarization field, the expansion history, and the matter content at the same time. When Planck data were analyzed within cosmologically coupled Bianchi 7H models, no evidence for such a background was found, and the present ratio of vorticity to the Hubble expansion rate was constrained to less than about 8 parts in 10 billion for that class of models. This limit should not be interpreted as a proof that every conceivable form of cosmic rotation is exactly zero. Observational limits always depend on the family of models being tested, the assumed matter fields, the treatment of perturbations, and the datasets included. It does show that any rotation resembling those specific homogeneous anisotropic models must be extraordinarily weak compared with cosmic expansion. More recent work continues to test alternative rotating backgrounds, partly because a small rotation has occasionally been proposed as a possible influence on modern cosmological tensions. Yet a fully relativistic analysis published in 2025 found that current CMB observations again drive the present-day rotation parameter toward a negligible value and leave the inferred cosmological parameters close to those of the standard model. There is a quiet but important distinction here between a globally rotating background and the rotation that naturally develops inside the universe. Galaxies spin, galaxy clusters contain orbital angular momentum, cosmic filaments may host coherent flows, and nonlinear gravitational collapse can generate vorticity in matter and gas even when the early background has none. The standard cosmological model does not predict a universe empty of curls and eddies. It predicts that these motions arise locally from structure formation rather than descending from one primordial cosmic axle. Cold dark matter begins, to a very good approximation, with an irrotational velocity field in the linear regime. But once streams cross and halos collapse, the effective velocity field becomes more complicated. Ordinary gas can develop vortices through shocks, pressure gradients, turbulence, and feedback. None of these phenomena establishes that space-time itself is rotating globally, just as whirlpools in separate oceans would not prove that an entire planet's surface is one continuous vortex. Local frame dragging must also be kept separate from cosmic rotation. A spinning star or black hole slightly twists the inertial frames around it, an effect predicted by general relativity and measured near Earth with gyroscopes and satellite observations. But the influence diminishes with distance and is sourced by a particular rotating mass. A globally rotating cosmology would instead concern the behavior of the large-scale matter flow and spacetime as a whole. Even the phrase total angular momentum of the universe is mathematically delicate. In ordinary mechanics, angular momentum is defined relative to an origin and conserved when external torque vanishes. But a cosmological spacetime may possess no unique external reference frame, no spatial infinity resembling that of an isolated system, and no universally preferred origin. General relativity offers well-defined notions of angular momentum in certain symmetric or asymptotically flat situations, yet assigning one global number to the entire universe is not always possible or unique. Cosmic rotation is therefore tested less by imagining a total spinning mass, and more by measuring vorticity, shear, preferred axes, and directional correlations in observables. Reports of unusual alignments among galaxy spins, quasar polarization, radio sources, supernova expansion measurements, or CMB multipoles continue to motivate investigation. But each signal must survive corrections for survey geometry, foreground contamination, calibration drift, selection effects, local motion, and the fact that statistical significance can change when a preferred axis is chosen after the data are examined. Some anomalies may eventually reveal physics beyond the simplest cosmological model. Others may prove to be chance patterns within one observable realization, or artifacts created by how the sky was measured. The present evidence does not support the claim that the entire universe rotates around a common axis, while it remains scientifically reasonable to place increasingly sensitive limits on possibilities that have not been excluded in every mathematical form. The most accurate answer is therefore neither an imaginative yes nor an absolute metaphysical no. General relativity allows rotating universes as mathematical possibilities, and observations permit only rotation weak enough to hide beneath stringent constraints in the models tested so far. The cosmos around us is filled with spinning structures, but when their local motions are averaged across the largest accessible scales, the deeper background appears remarkably indifferent to direction. Space expands, matter gathers, galaxies turn, and black holes drag nearby frames, yet no confirmed universal hand has been found beneath those motions, guiding every orbit around one invisible center. If the universe carries a rotation at all, it is not the grand and obvious turning of a wheel in the darkness. It is a whisper so faint that the oldest light in existence has so far answered mainly with stillness. The final answer is not that the universe lacks order, and it is not that every direction is random, but that there is no single confirmed direction of rotation shared by all things. Instead, the cosmos is filled with nested memories of motion, each one inherited from a particular cloud, disk, collision, gravitational encounter, or region of the cosmic web, so that agreement appears locally, breaks gradually with scale, and finally dissolves into statistical diversity when the view becomes large enough. If we begin close to home, the pattern seems almost persuasive. Earth turns on its axis. The moon moves around Earth. Earth moves around the sun. And the other major planets follow the same broad orbital direction when the solar system is viewed from above the sun's north pole. That harmony is real, but it is also conditional. Viewed from the opposite side, every apparent clockwise motion becomes counterclockwise, while the physical system remains unchanged, which means that left, right, clockwise, and counterclockwise are never complete descriptions by themselves. The deeper quantity is angular momentum, represented by a vector perpendicular to a plane of motion. And what can be compared meaningfully is whether two such vectors are aligned, tilted, or opposed. Within the solar system, the orbital angular momentum vectors of the 8 planets are closely aligned because those worlds formed inside one rotating protoplanetary disk. Their common motion is therefore not evidence of a universal cosmic command. It is evidence of common ancestry. The disk from which they emerged inherited a small net rotation from turbulence, asymmetry, and gravitational torque in the molecular cloud that formed the Sun. As the cloud collapsed, its radius decreased, its rotation became dynamically important, and matter flattened into a disk, because collisions and radiation removed energy more readily than they removed angular momentum. The planets assembled within that disk and carried forward its dominant direction. But even here, the agreement was never perfect. Their orbital planes are slightly inclined to one another, their eccentricities differ, and their spin axes preserve separate histories. Venus rotates slowly in a retrograde sense. Uranus lies almost on its side. Mercury occupies a 3-to-2 spin-orbit resonance. Earth's rotation has been slowed by lunar tides, and the giant planets turn with very different periods and internal structures. These differences reveal an important hierarchy. The angular momentum of a planet's orbit around the Sun is much harder to reverse than the angular momentum of its rotation around its own axis. A collision powerful enough to overturn a world may still leave its path around the Sun largely unchanged. The farther we travel from the planets, the more clearly this hierarchy appears. Regular moons often move in the same direction as their planet's rotation because they formed inside circumplanetary disks, while irregular moons occupy inclined, eccentric, and retrograde orbits because many were captured rather than formed in place. Triton circles Neptune backward relative to the planet's spin, probably because it arrived from the outer solar system and was captured through a complex gravitational encounter. Comets from the distant Oort cloud can approach the Sun from almost any direction because their once flatter orbits were scattered outward by the giant planets and later reshaped by passing stars and the tidal field of the Milky Way. The solar system is therefore not one wheel, but several dynamical populations superimposed upon one another, each preserving a different chapter of formation and disruption. When we look at other stars, the same logic survives, but the range of outcomes grows much wider. Many multi-planet systems are remarkably flat, with several worlds crossing their stars along closely aligned planes, suggesting that they preserved the geometry of their natal disks. Others contain giant planets on steeply inclined, nearly polar, or apparently retrograde orbits relative to the spin of the host star. These configurations can arise through planet-planet scattering, gravitational forcing from distant companions, tilted protoplanetary disks, high eccentricity migration, or long-term tidal evolution. The measured misalignment does not always reveal which component moved. The planet may have changed orbit, the star may have changed orientation, or the entire disk may have formed at an angle. Once again, the system's present direction is not a simple label, but the final result of many exchanges of energy and angular momentum. On galactic scales, the language of one shared direction becomes even less adequate. Most stars in the Milky Way's thin disk participate in a dominant rotation around the galactic center, yet they do not move like points fixed to a rigid plate. Each follows its own orbit through the gravitational field of stars, gas, the central bulge, the galactic bar, and the dark matter halo. Some stars move on eccentric paths, some oscillate far above the disk, and some halo populations travel in a retrograde sense, likely because they were deposited by smaller galaxies consumed long ago. Gas can rotate differently from stars. Central regions can be misaligned with outer disks, and entire counter-rotating components can coexist inside one galaxy. A galaxy, therefore, has a net angular momentum and a recognizable average direction, but not every constituent obeys that direction. The same principle extends to galaxies themselves. Their spins are not distributed in complete isolation because galaxies grow inside the cosmic web, where matter flows along sheets and filaments under the influence of large-scale tidal fields. Neighboring galaxies can show statistical alignments with one another or with nearby filaments, and simulations often predict that the preferred orientation changes with mass, merger history, and environment. These tendencies are scientifically meaningful because they reveal how structure formed. Yet, they are regional correlations rather than proof of a universal spin. A galaxy in one filament may acquire angular momentum along the filament. Another may be turned across it by mergers, and a third may later be rebuilt by gas arriving from a new direction. Claims that spiral galaxies show a large-scale excess of one apparent-handedness remain debated because the result is sensitive to image classification, survey geometry, mirrored data, statistical choices, and the distinction between visible arm winding and true three-dimensional rotation. At present, no broadly accepted observation demonstrates that galaxies throughout the observable universe rotate around one common axis or favor one universal sense of spin. The final scale is the most difficult, because asking whether the universe itself rotates is not equivalent to asking whether an object turns inside space. The universe includes the space, matter, radiation, and reference frames required to define the motion. General relativity permits mathematical cosmologies with shear, anisotropy, and vorticity, including famous rotating solutions such as Gödel's universe and broader families of Bianchi models. But mathematical possibility is not observational confirmation. A rotating cosmic background would be expected to leave coherent directional signatures in the expansion history, in the distribution of structure, and especially in the temperature and polarization patterns of the cosmic microwave background. Measurements of that ancient radiation show that the universe is remarkably isotropic on large scales, with only very small fluctuations around the average. Some large-angle anomalies continue to attract careful study, and no finite set of observations can exclude every imaginable rotating geometry. But current data place extremely tight limits on global rotation in the best tested models. The scientific conclusion is therefore precise rather than absolute. The universe contains rotation everywhere, but no convincing evidence shows that all of those rotations descend from one cosmic axis. The order we observe is generated locally. A collapsing cloud preserves its angular momentum and creates a disk. A disk gives planets a shared orbital direction. A planet creates a smaller disk for moons. A galaxy gathers spin from tidal torques, inflows, and mergers. A filament influences the orientations of galaxies growing within it. At every level, matter remembers where it came from and how it arrived. Yet those memories do not have to agree with memories formed elsewhere. This is why the universe can look both organized and free, structured without being synchronized. The same conservation laws operate in every region, but they do not demand the same initial conditions. The same equations govern every rotation, but they do not select one universal orientation. And so, while the room around you seems motionless, you are being carried through several overlapping currents at once. Earth turns beneath the atmosphere. The planet travels around the sun. The sun crosses the Milky Way, and the Milky Way moves among neighboring galaxies within the expanding cosmic web. None of these motions requires an absolute left or right. None needs the universe to rotate as one body. Their coherence comes from the quiet persistence of physical law, while their diversity comes from history. The deepest answer is therefore not simply that everything spins differently, but that every spin is a record. Some records were written together and remain aligned. Others were tilted by tides, rewritten by collisions, or inherited through capture and merger. The universe is not a single wheel turning in one direction through the dark. It is an immense archive of motion, with rotations nested inside rotations, each preserving a local past, all unfolding beneath laws that remain steady even when the directions do not. As you drift back into the quiet of the night, remember that the universe does not move in one single direction, but through countless ancient motions woven together. Thank you for traveling with Sleepy Space. If you enjoyed this peaceful journey, please like the video and subscribe to the channel for more calming explorations of the cosmos.